Hello everybody, welcome to the second mini lecture on modules. In the first lecture, in case you haven't seen the first lecture, in the first lecture we have introduced modules. We have looked at the axioms. I have the axioms for modules still written in this box over here. So in case you haven't seen the first lecture, maybe pause this video now and go to the first lecture and see how a module is defined. And we have also discussed some examples, of course. And what we're now going to do is we're going to introduce quotient modules. And this is, of course, a concept that you sort of know if you know some group theory or if you know some linear algebra, because in group theory you have looked at groups and normal subgroups of these groups, and you mod it out by normal subgroups to get quotient groups. And in linear algebra you have similarly looked at quotient vector spaces and so on. In ring theory you have looked at factor rings. And we're going to do basically the same now for modules. So let's say our module is again called M. Can you see this now? So M is again our module, and now inside M is another module, N. So N is a subset of M, and N is also an abelian group and satisfies these axioms for a module. So N is a submodule, meaning in particular it is an abelian group. You know, every abelian group is of course a normal subgroup, so you can talk about the quotient group M mod N, and we want to establish that this quotient group is or can be endowed with the structure of a module. Just in case it's been a long time since you have looked at quotient groups or related concepts, let me quickly remind you what this was. So you start with, let's say for now M is just a group. So this is just a reminder on how quotient groups were defined. So M is your group, and now you establish an equivalence relation on this group. Namely, you're saying A1 is equivalent to A2 in this equivalence relation. So A1 is in the same equivalence class. This is a way to say it. A1 is in the same equivalence class as A2 if and only if A1 minus A2 is an element of N. And you can see that this indeed, you can check that this defines indeed an equivalence relation. So A1 minus A1 is 0, which is an N, since N is a group which contains, of course, 0. Since every group has to contain a 0 element, and so on. You can switch these around, and here also. And since this is a group, the additive inverse is in there, and so on. So so this is the equivalence relation, and this is what M modulo N, this quotient group, is. It is the set of these equivalence classes you get in this way, and on this set of equivalence classes you declare addition simply by saying, so let's say the image of A1 under the projection to the equivalence class is called, as is usual A1 bar, so A1 bar plus B1 bar, which is to say I'm now going to remind you what the addition operation on this quotient group was. So A1 bar plus B1 bar is simply defined by A1 plus B1 bar. So you add two equivalence classes, A1 bar and B1 bar, by first adding their representatives and then going to the respective equivalence class. And of course you need to check that this is well defined, meaning if you pick another representative, so for this in this class, so if you have A2 bar is the same as A1 bar and B2 is the same as B1 bar, so A1 is one representative of this equivalence class and A2 is another one, and the same for B1 and B2. Then of course you have to check that this addition is well defined, so you need to know that A2 plus B2 bar, which is, as we have just defined it a moment ago, A2 plus B2 bar. This has to be in the same equivalence class as, or has to be in the same equivalence class as this one. But this is easy to see because this being the same, so this is what we are asking, is this the same? Well, what we need to check is the following. A1 plus B1 minus A2 minus B2. Is this an element of n? Because, as I have just reminded you when we started to talk about this concept, two elements are in the same equivalence class if their difference is in n. So A1 plus B1 gets sent to the same equivalence class as A2 minus B2 if their difference is in n. But look, this is easy to see because A1, this is nothing but A1 minus A2 plus B1 minus B2. But A2 and B2, I mean A2 and A1 are in the same equivalence class, so A1 minus A2 is in n, and the same is true for B1 minus B2. So this is in n. This is another n. This is a sum of elements in n. So this is an element in n. So we see that indeed addition is well defined, and now this was just review because what we have done up to now is just pure group theory. We now need to look at the other axioms, because for our module we did not only need an abelian group, but we also need the multiplication with this ring R. So we need to see that R times A bar, first of all we need to define this. So we define this in the following way. We say R times A bar, this is just R times A bar. And again we need to check that this fulfills the axioms. So let's see, we have R times A bar plus B bar. And we want to say that this is the same as R times A bar plus R times B bar. So we need to get from here to here. So this is by definition R times A plus B bar. Now, using this axiom, we can say this is the same as R times A plus R times B bar. And this is, by the way, we have just introduced addition on this quotient group a moment ago. This is R times A bar plus R times B bar, which is, again, by the definition of addition, the same as this. So we have checked this axiom, and yeah, technically we also need to check this axiom, which I shall leave for you as an exercise, since my board is already full. But I think at this point you believe me that this structure M module N is indeed a module, and this will become important in the next lecture, because in the next lecture we will look at homomorphisms of modules, and we will meet an old acquaintance, namely the first isomorphism theorem, and we will express this, of course, in this language of quotient modules. So, thank you for watching. If you like this video, please give a thumbs up or subscribe to the channel. If you have questions, please comment below. And thank you for watching. See you next time.